topic of today's video is going to be molecular and ionic compounds. So what we're doing is we're just introducing each type of compound here. Ultimately, the goal here is to be able to identify them and be able to create them so that when we can then name them. So ultimately, we want to learn how to name these things. So that's what we're going to be working on in class come Friday. So a molecular compound, by definition, can be identified because it's a nonmetal, as we've learned in the periodic table, combined with another nonmetal. Just quickly, nonmetals are found to the right-hand side of the periodic table. Metals, on the other hand, are found to the left-hand side of the periodic table. So, an ionic compound, in contrast, is going to be a combination of a metal and a nonmetal. So again, if we see two nonmetals together, we know that's a molecular compound. If I see a metal coupled with a nonmetal, I know that's an ionic compound. All right, so the driving force to form these compounds is essentially going to be similar, and we're going to get to that in just a moment. So the next thing I want to look at is the understanding that atoms typically like to carry charges in order to be stable. Okay, there's a driving force for this. If we remember from our discussion of the periodic table, anything that's found over in group 8A is very stable. Those correspond to our noble gases, which are sometimes called the inert gases. They're called that because atoms of the inert gases tend not to want to react with anything, meaning that they are electronically stable. All right, so what I'm going to do is I'm going to just pick one particular group of the periodic table, and I'm going to go through the main group here. So I'm going to leave the transition metals out. So I'm going to look at group 1A all the way through group 8A. Okay, again, I'm leaving the B group metals, which are the transition metals, out of this for the time being. We can come back and talk about those later. So what I'm going to do is I'm going to pick one row within these main groups. So I'm going to look at row number 2 in the periodic table going across, starting with lithium all the way across to neon. Now, if we look back in our periodic table section of the text, what we'll actually see is that lithium and beryllium will be characterized as metals. Boron is actually a metalloid, which means that it has properties of both metals and nonmetals. And then everything to the right of boron in this particular row would be a nonmetal. That's carbon all the way through neon. All right, so here's the situation. What I would like is for each one of these things, in terms of the number of electrons that it has, to look like a noble gas. It can look like its next nearest noble gas. That's the goal. So how are we going to get there? Well, if the goal is for each atom to look like a noble gas, then that atom has to either gain or lose one or more electrons in order to look like its nearest noble gas neighbor. And again, the noble gases are found over in group 8A. Things like helium, neon, krypton, argon, those types of elements. They're stable, so we want everything else to look like those in terms of the number of electrons that they have. All right, so if I take a look at this, the number of electrons that we've got in each one of these particular elements, as far as the ones that we can either gain or lose, are going to be dictated by the group number. So lithium, of course, will actually have an electron that we can either gain or lose to work with. All right, so what I'd like lithium to do to form an ion is to look like its next nearest noble gas. Now, lithium has two options. Lithium can either lose one electron to go backwards and look like helium, or it can gain 7 electrons to go forwards to look like neon. So in this particular case, it's a lot easier to lose 1 electron than it is to gain 7 electrons. So as a result, I'm going to take an electron away from lithium to make it look like helium. So as a result, the ion that we would get would be a lithium 1+. Why 1+? Because I started out with lithium neutral, and I stole 1 electron from it, so now it actually has to carry a unit 1+ charge, because I have 1 more proton than I do electrons left over. All right, so what about beryllium? Beryllium, again, has a choice. It can lose 2 or gain 6. It would rather lose 2, so as a result, the beryllium ion would carry a charge of Be2+. Boron looks like it would rather lose 3 than gain 5. so that means I'm going to have a boron 3 plus here. Carbon, we're splitting the difference. So if we had to assign a charge to carbon, we could say that it could either be 4 plus or 4 minus. How about nitrogen? Well, now we are moving in the opposite direction. Nitrogen would actually rather gain 1, 2, 3 electrons to look like neon than lose 5. Okay, so as a result, nitrogen is going to pick up 3 extra electrons to give it a net charge of 3 minus. Oxygen, as you can see, would rather pick up 2 than lose 6. So the oxide ion would actually have a 2 minus charge. Fluoride ion would be a 1 minus charge because, again, it wants to pick up just 1 electron to look like neon as opposed to losing 7 to look like helium. And then ultimately, we don't put a charge on neon because it's already stable and happy. All right, so these would be the specific ions that we would make in order for each one of these types of atoms to gain stability. All right, so again, how do I do this? Well, there are 2 ways to accomplish this. So one way to do it is by physically gaining or losing electrons. So for something to gain electrons, that atom has to steal those electrons from somebody else. Okay, so for example, if I take a nonmetal which wants to gain electrons and put it in close proximity to a metal which wants to lose electrons, well then that nonmetal can steal those electrons from the metal and form 2 charged species. That's how an ionic compound is actually formed. The other option is for sharing of electrons to take place. So in this situation, I have 2 nonmetal situations here, and these 2 nonmetal atoms may come together, and not one has enough of a desire to steal electrons from the other, so they're better off by sharing electrons. So sharing electrons in the case of a covalent or molecular system in which we have 2 nonmetals coming together is another option by which we can satisfy this requirement of each element looking like its nearest neighbor noble gas. All right, folks, so let's take a look at a couple of examples of both ionic and molecular situations here. So, in the case of an ionic example, again as a reminder, this is a metal combining with a nonmetal. All right, so a good example of this would be a sodium ion combining with a chloride ion. Now in this case, we know that sodium, if we go back and look at our periodic table, is in group 1A. Chloride is in group 7A. Now, we know that group 1A things have a tendency to lose 1 electron. That's where the 1 plus came from. Group 7A elements or atoms have a tendency to gain 1 electron. That's where the 1 minus came from here. Now, if a sodium ion comes into proximity with a chloride ion, there's going to be an electrostatic interaction or attraction between those 2 things because they're oppositely charged. And we know that opposite charges tend to attract. So when these 2 things find each other, they're going to come together to form this electrostatic bond or interaction between the 2 of them. So one thing that we have to understand here is for them to make a unit here, the charges have to cancel out. And in this particular case, that happens. Notice that the 1 plus on the sodium ion cancels with the 1 minus on the chloride ion. So this would actually be a unit formula for this particular ionic compound. Now, let's take a look at another example. If I have the calcium ion combining with a chloride ion, things are going to be a little bit different here. Calcium ion is in group 2A in the periodic table, which as we just saw, group 2A species have a tendency to want to lose 2 electrons to look like their next nearest noble gas neighbor. Chloride is in group 7A, so chlorine wants to actually gain 1 electron to carry the 1 minus charge as we saw before. Now, if I find a calcium ion and bring it into proximity with a chloride ion like this, notice what's going to happen. We're going to get an imbalance of charge. We're still going to have this electrostatic interaction between the 2, but now I need to balance that charge between the 2. The way that I'm going to do that is I'm going to add 2 chloride ions for every 1 calcium ion. And if I do that, I'll put a little subscript 2 down here in the formula to represent that. That means I have 2 chlorides per 1 calcium. Notice what happens to the total charge on the chloride. 1 minus times 2 gives me a total of 2 minus charge. Now you'll see that the 2 plus on the calcium is going to balance out with a total 2 minus on the chloride. So the formula unit for calcium chloride would be CaCl2. We could do the same kind of argument for aluminum combining with the bromide ion here. So aluminum is in group 3A. It's going to lose 3 electrons to give us a 3+ charge. Bromine is over in group 7A. It's going to gain 1 electron to form Br1 minus. And again, when we bring these ions together electrostatically, we have to have charge balance. So it's obvious in this situation that I need to utilize 3 bromide ions for every 1 aluminum ion. And again, I'll specify that down here by putting a subscript 3. So now I have a 3+ here. The 1 minus times the 3 bromides gives me a 3 minus. The 3+ and the 3 minus cancel to give me charge neutrality. So the unit formula for the ionic AlBr3 is this. It's Al coupled with 3 bromides. So that would be our formula. Now, another option that we can look at, we can take something from group 2A like calcium. Wants to lose 2 electrons to give me a calcium 2+. Combine that with something from group 6A like oxygen, which wants to gain 2 electrons to form O2-. Now in this case, if something with a 2- charge finds something else with another 2- charge, notice what happens. The 1 ion of calcium will combine with the 1 ion of oxygen, and in this case the 2+ and the 2- will cancel, so my unit formula for the ionic calcium oxide is CaO. Alright? So in either case, these are ionic because there was actually an exchange of electrons taking place here before the bond could actually be formed. So in other words, in this particular case, the chlorine actually stole an electron from the sodium ion to give the sodium ion a positive charge and the chlorine a negative charge. And then once that conversion was complete, then those 2 ions found each other to form the unit cell. Now the other option that we have is the molecular or covalent example. And again, just to reiterate, this is when we find one nonmetal coupling with another nonmetal. And a good example of this is the formation of diatomic hydrogen. We talked about in class how hydrogen is found in nature's H2, not as hydrogen atom. And the reason for that is to gain stability. Notice that each hydrogen has just 1 electron in it, right? Because hydrogen actually just has an atomic number of 1. So as a result, each hydrogen will have 1 proton and 1 electron. Now, we want our hydrogens to look like helium. Helium is the noble gas neighbor, next nearest one. So as a result, one hydrogen doesn't have the power to extract an electron from the other, so the best option for the 2 nonmetals here is to share electrons. So what we end up with is a hydrogen bonded to another hydrogen, where each hydrogen brings in 1 electron. But then what happens is each hydrogen can lay claim to the pair of electrons. So now this hydrogen can have its 2 electrons to look like helium. This other hydrogen can also have its 2 electrons to look like helium. Another good example of this would be a hydrogen atom bonding with a fluorine atom. Hydrogen has 1 electron associated with it. Fluorine, all right, has 7 electrons associated with it because it's over in group 7A, so these are the electrons we care about. So as a result of this, what's going to happen is when we bring these things together, hydrogen will bring in its 1 electron, fluorine will bring in its 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 electrons. And now what's going to happen is we're going to be sharing electrons between those 2, so that now hydrogen can have its 2 electrons to look like helium, and the fluorine now can have its 8 electrons to look like neon, which is its next noble gas neighbor. All right, so next time in class, what we're going to do is we're going to learn how to name these compounds. See you next time.